Okay, we have known for a long time that F net equals MA, okay? And we have just introduced a rotational equivalent of this. We have tau equals I alpha. All right, so we also learned just recently that there is a different way of writing this by defining momentum, lowercase p, is equal to mv, such that we can then say that F net is equal to dp dt. Okay? So this was a very powerful way of looking at Newton's second law. So again, this is just Newton's second law, where we have defined this momentum to be mass times velocity, and therefore the time rate of change of that is force. Okay, and we found for many things, collisions, explosions in particular, that the time is so small that any external forces that are real don't contribute. They're insignificant for that small amount of time, such that momentum is conserved. If we observe a very small time interval, looking at just before to just after an interaction. This is very powerful. So the question is there something equivalent for rotation? And the answer is yes, there is. If we define something called angular momentum, which we use an uppercase L for, and we call that I omega, okay, and look at the similarities, just like the similarities here. Here's force, here's rotational force. Here's mass, here's rotational mass. Here's acceleration, here's rotational acceleration. Oh, and I should put a net there. That should be net torque. Okay. So same thing here. This is momentum. This is angular momentum. This or rotational momentum. This is mass, rotational mass, velocity, rotational velocity. And so with that in play, we can get, it's not as quick to get this just looking at this one, but I'll show it in a second. We get that tau net is equal to dl dt. And we have another conservation law called conservation of angular momentum, which is just conservation of momentum, but applied now to objects that have extended mass, where their mass is distributed, a disk, a wheel, a sphere, instead of just point particles, which we applied here. Okay? So a goal is to try and see some, really understand what this angular momentum is and different ways to look at it. Now, one way to look at it and to see how we can come up with this from this one is one way to define angular momentum is the particle way. So how we would kind of do everything we've done with like moments of inertia, we start with just simple point particles and integrate all their positions. Same thing kind of here. We can look at the angular momentum of a particle, and that is defined as R cross P. Okay? And remember that this cross product has a size that is equal to RP sine of the angle between them. But since it's a full vector, the direction is given by the right-hand rule, which I'm going to start to write this way. RHR with this hat over it. Okay, that's called, the hat means a direction only. It's like X hat, Y hat, J hat, which we've seen before. Okay, so this is just kind of my Dr. Hale's way of saying we get the direction by the right-hand rule, okay? And we find how big it is from this relationship. Remembering, too, that the cross product simply gets perpendicularity. So I can write that as R perp P, meaning I take P and find out the component of R that's perpendicular to P. That's the same thing as doing the sine of theta. Or I can write this as RP perp. If that's easier for the situation, if it's easier to find the piece of P that's perpendicular to R, I can do that as well. Okay? So in doing this, again, direction is given by the right-hand rule. With this definition, okay, then I can look at torque. With its definition, torque is, well, let me just look at one torque on a particle right now. The torque is R cross F, but F is ma, but A is dv dt, and I could take that d by dt out in front of all of it, and I can get d by dt of r cross mb. Okay, well that's just p, and that's the definition of angular momentum, so we get dl dt. Okay, so that's the way of showing this result. But what's so beautiful about it is it's great to know the math, and it's important to know the math, especially if you want to try and expand it to more difficult, more complex problems. But the end result has this beautiful symmetry between linear things that are being pushed along the line, versus rotational things. So we have our definition of force or torque, definition of momentum or angular momentum, and then how those are related. Okay, so remember, this is how you'd find the angular momentum for a particle that's moving with momentum p. And this could even be moving in a straight line, by the way. The p doesn't have to be a particle moving around in a circle. We could apply this to that, but this could also be applied to a particle moving in a straight line. And I'll do an example in a later video that shows that. The important thing is that any object with momentum, including things that are spinning, or generally usually things that are spinning, will have an angular momentum. And so we can then take this, and if we integrated this over all the pieces of an object, we'd get this one. So this, by integration, would become I omega. Okay. So this is one definition. We use this one for an extended object like a disk or something like that. We use this definition for a point particle.